so everyone can see my screen? Perfect. All right, that's not the presentation. That's the one. All right, so as you guys know, the attendance is mandatory. There's going to be 6 labs in the course. The first one is the one we're having today, and it's going to be an HFSS and ADS workshop. Labs 2 to 5 will be on various transmission lines and antennas using both HFSS and ADS, and then lab 6 will be an HFSS exam, and we'll let you guys know more about that later on. So the first lab will not have a report, so that's today's lab, but labs 2 to 5 will have reports, and the report guidelines will be uploaded after each lab. The lab reports should be typed on LaTeX, and if you guys are not familiar with it, there is a good tutorial on overleaf, and it should be typed using IEEE 2-column format, and I provided here a link, which is also on CLearn, to some of the templates that you can use. The reports will be due 1 week after the lab at 11:55 p.m., except of course today's lab. Office hours will be by appointment on Zoom. The details of the meeting is on CLearn. So if you guys want to meet, just send me an email beforehand, and we can chat. All right. So, okay. Yeah, so I use Tech Studio, but there are a lot of other software that you can use. Overleaf is the easiest because you can access it from anywhere, but I generally prefer Tech Studio. Does that answer your question? No problem. So I can show you guys what it looks like. This is the one that I like to use. It's called Tech Studio. You type in the LaTeX stuff here, and then you see the PDF here, and that's what you would submit. Again, if you no, okay, now you can. Okay, so you can see the LaTeX, the Tech Studio window. Okay, all right. So that's what I like to use, but you can also use anything else, as long as you submit a PDF with the 2-column format. And again, the link on here, there's a lot of templates that you can use. So Basil, is there a delay still between the screen and what you can see? Okay, so again, if everyone is experiencing that delay, I will try to slow down. And again, if you're finding it a bit hard to follow along, this is recorded, so you'll be able to visit it later on. But let me know if the delay still persists, especially when I'm doing the workshop. You can't see the screen at all? Okay, I'm gonna go back to okay, so if you guys can't see my screen, try to rejoin. I'm gonna give you a few minutes, and then we'll resume again. Basil, can you see my screen? Okay. Okay, maybe I'll reshare it. Okay, maybe I'll stop sharing and share it again. Okay, I stopped sharing. I'll do it again, and we'll make sure that everyone can see it. Okay, Basil, just monitor the chat for me. If there's any issues, just let me know, please. Okay. Okay. So there might be different delays for different people. Again, I will try to slow down, and again, the session is recorded. So if you're having trouble following along, it will be available by tomorrow because it takes some time to upload it on YouTube, and then you'll be able to see it fine. Okay, so we'll move along, and hopefully the issues gets resolved as we go. The software that we're going to use a lot this semester is called HFSS, and it stands for High Frequency Structure Simulator, and it's used to analyze structures electromagnetically. So for example, you can analyze transmission lines, antennas. You can analyze the radar cross-section of aircraft, and a number of other structures. The numerical technique that HFSS uses is called finite element method, and although you don't need to know exactly how it works, it's a good idea to understand how HFSS solves Maxwell's equations in these structures. So the idea is the software will divide each structure into a smaller structures called tetrahedra. So kind of like the picture on the bottom left-hand corner here. And then it would solve Maxwell's equations at every one of those small structures. And then it would use an adaptive meshing process to try to get an accurate solution. And the accuracy of the solution depends on the convergence criteria that the user sets. So when you run the simulation, you would tell HFSS what you consider as an acceptable margin of error, and we'll discuss that today when we run the sub-simulations. All right, so I just switched my screen. Can you guys see that switch, or is it still delayed? Okay, so I'll keep that in mind as I switch between slides and while I'm running the simulations. All right, so the HFSS design process has a number of steps, and while you're starting to use the software, it's a good idea to keep those in mind, just to make sure that you're doing everything right. So the first step is to design the structure. So it's going to be a 3D model of your design, and for that you just use HFSS CAD-like drawings, so you can draw rectangles, circles, etc. And then after you design the structure, you want to define the electromagnetic boundaries around that structure. So for example, you can define the boundaries to be metallic, or you can have an open boundary to free space. The next step is to define excitations, and these are the ports through which the energy is going to flow in and out of your structure. So for a transmission line, that would be the input and the output of the transmission line. The next step is to define the solution frequency and the convergence criteria, and at this step, that's where you tell HFSS what you consider as an acceptable margin of error in the meshing. After that, you would usually set a frequency sweep. So a lot of times you want to look at the results in a certain frequency range. So you would set the frequency sweep that you want to look at. Then you validate the design. So this is just clicking a button to make sure that you've done everything right. Then you simulate it, and then you plot the results that you want to see. So any questions on that? Okay. So for the solution types, there are a number of them, and I'll let you guys read on that on that later on, but the one that we're going to use in this course is the default solution type, and it's called driven modal. And the differences between them are, you don't need to know them, but for example, the driven modal, you have to set an excitation in HFSS, but the eigenmode, it would calculate the modes inside a structure without you having to set an excitation. But in any case, the default mode is a driven mode, and that's the one that we're going to use throughout the course. In terms of excitations, there are two main ports that you can define, and those are the wave port and the lump port. The main difference between the wave port and the lump port is where you define it. So for a wave port, it has to be applied to the edge of the solution space, while a lump port can be applied inside the solution space. And I do believe for most of the structures we're going to design, we're going to be using wave ports, and that's what I will show today. But if we do need to go into lump ports, I will explain it later on. Alright, so for the frequency sweeps, there are three main types, and I'm not going to go through every point here because I will upload this presentation on CLearn so you guys can take a look at it. But the key takeaway is the fast sweep is the fastest, but it's also the least accurate frequency sweep. The main benefit of it is you can run a large number of points without having to wait for a large simulation to run. And one of the key benefits is that it would provide field data at every point. But again, you have to be careful because it's not the most accurate solution. I generally don't use it. I would use it at first to just have an idea of what the response of the structure looks like, and then I would go on and run other more accurate sweeps. The next type of sweep we have is the interpolating sweep, and that's the one that you will use most often. It's fairly accurate, and it's very good for broadband responses, so you can run a very large frequency sweep, get good results without having to wait for a long time. The only downside of the interpolating sweep is that you don't get field solution data, and for that you would have to run the next type of sweep, which is discrete. So that'll be the next one. The discrete sweep is the most accurate, but it also takes a very long time. So what would happen in a discrete sweep is HFSS will solve it will solve the structure at every single frequency. So that can take a very long time. So you have to be very careful when you use the discrete sweep. You generally want to run it for just a few points, so like 5 to 10 points, not more than that. But the best thing about the discrete is that it provides field solutions as compared to the other ones. So the main takeaway here is you would mostly want to use interpolating unless you want field solutions, and for that you would go to the discrete sweep. So any questions about the sweep types? So we'll see that again while I'm running the simulations. So if it doesn't make sense now, I'll go over it again. All right, so with that being said, let's do some more exciting things. So we'll go on HFSS and we'll design rectangular waveguides, a microstrip line, and if we have time, we'll go into a coax cable. In the next few slides, I have the dimensions of the designs we're going to use, but I do have them written down so you don't have to remember them. So with that being said, I'm going to go on the server now, and I'll ask you guys to do the same. So I'll give you guys 2 or 3 minutes to get into the server if you haven't, and we'll start back in a minute or two. So basically, you can see my screen on the server. Okay. So 1 or 2 minutes, and then we'll start HFSS. Yeah, please let me know if there's a question. Yeah. So I will do that in a second. So if so it's usually on the desktop, but I will run it right now. So if I haven't done that yet, if that's what you mean. They can't move their mouse. I don't know. Um, the only suggestion is try to disconnect from the server and get on again. Okay, I will suggest another server. Okay, so I will have a break between when I finish the HFSS to ADS. I don't know what time the break will be, but it will be about 5 to 10 minutes, and hopefully it will be like midway through the lab. But I can't promise. Maybe 4:20 we'll have a break. Yeah. So if you guys can access the server, it's fine. For those who are like, there was someone that cannot move their mouse, I will give you guys another server that you can try. Just a second. The problem is in accessing the server, or okay, Manar, try. I have an IP address written on the screen now, which basically you can see. Okay, so try to access that server instead and see if you can use the mouse. Any other questions, Basil? Okay, so again, if your mouse is not moving, I don't know what the issue is. You can email me about it if it still persists, and we can try to find a solution. But for now, I'm gonna assume that a lot of people are on the server and ready to go. So we'll start the software now. All right. So the software is under sort of an umbrella program, and it's called ANSYS Electronics Desktop. You should be able to find it on the desktop. If not, you can search for it here. So if you go ANSYS Electronics Desktop, you should be able to find it. So just click on that. So when you get this window, if you've used HFSS before, you may not get this window, but I'm going to go through it so that those who haven't used it before can follow along. So the project directory, that's where you want to save your project. I know in the document about the remote access, I told you guys to save everything to the H drive, but I think we've had some people who do not have an H drive yet or cannot access it. So for now, you can use the D drive on ELI. You just create a folder with your name and put the project in there until we figure out what the problem is with the H drive. So for now, I'm going to go and save this on my H drive. So those who have H drive can follow along. If not, again, you can use the D drive instead. So you can go on your H drive and you can create a folder for the course. right, so that's going to be the directory where you save your project. The temporary directory, you can leave it as is. That's not a problem. And this option, leave it up to you guys. And hopefully in a second or two we should see the software. All right, so you can close this message. So as you can see here, by default a project was created, and if you click on the project and look down here, you're going to see that the location where it's saved. So for us it's saved on the H drive where I located it. So you can name that project, give it a meaningful name. So I'll call it Lab 1 HFSS Workshop. Okay. Where is it frozen? Is anyone else having that problem? Okay, so I guess there's going to be some delays. I guess that's inevitable. Okay, yeah, give that a shot. And again, I know it can be frustrating, but the session is recorded, so if you can follow along as much as you can, and then watch the video later on, that's another option. Okay, so for those that are here, so we have a project. Under this project, we can create a number of designs that are under ANSYS. We're only interested in HFSS, so if you go on the top here, in the desktop menu, you can add an HFSS design. So if you just click on the arrow and then click on HFSS, that will add an HFSS design to your project. So as you can see, the solution is the driven modal, which is the default. If you guys are interested in looking at the other ones, if you go under HFSS solution type, you can see the solution types that we can define, but we're only going to run the default driven modal solution. No, so when the default, there's going to be a project created by default, but you can create a new project as well. So if you go under new, if you just click new, it will create a new project. But if there's already a project in there, you can just rename that to whatever you want. So I'm just going to go over this again with the new project. So I will delete this one and just do the project again so that everyone is on the same page. So I'm going to delete that. No problem. All right, so a new project is created. I'm going to give it the same name as before. And once you have created the project, you can then add an HFSS design. So if you go under desktop, HFSS, and then HFSS. All right, so once you've created an HFSS design, you can rename it. So the first design we're going to make is the rectangular waveguide. So you can call it So over here, this is where you're going to place your design. This is going to be the project. This is going to be one of the designs in that project. So the first step in any HFSS design, as I mentioned before, is to create the 3D model of your design. So for a rectangular waveguide, there's only one structure that we need to create, and that's just the rectangular box. So under draw, you can see here a number of objects that we can insert, or surfaces or lines, but we're only interested in a rectangular box, so you can go under draw box and click on that. And there's a number of ways that you can do this. You can move your mouse and look at the coordinates in the box, in the measure data box, and see where you want to start. You can go down here and enter it manually, but the best way to do it is to actually define your objects using variables. So when we're in this stage, we just want to put a box somewhere, and then we're going to change the dimensions later. So you can go ahead and click anywhere, and then do a second click to define the plane, and then a third click to create the box. So again, at this stage, it doesn't matter where you start the box and where you end it, because we're going to define the dimensions later on with variables. Alright, and as you can see, if you've done that, HFSS would have created by default a vacuum box, and the box is over here. The properties will show up in the properties window on the bottom left corner. So I always like to give my models a meaningful name so that they make sense later on. So for the name, I can call it waveguide. And then for the material, we're going to design an air box. Vacuum and air are very similar, but I'll show you guys how to change that to a different material. So by default, it's vacuum. If you click on here and go under edit, you can search for air, and then you'll see air here. So it's got relative permittivity is almost 1. Relative permeability is almost 1. Loss tangent is 0. It's pretty much lossless. So once you have air selected, you can press OK, and that will change the material to air. So now we have an air box, pretty much. Now the next step is to put the dimensions in. So if you go under Create Box, in the Properties window, you can see the properties of this box. So there is the starting position, the size in the X direction, the size in the Y direction, and the size in the Z direction. So let's say we want to create the rectangular waveguide so that it's centered on the origin. So now let's say it starts in the XZ plane, and it extends along the Y axis. So the face will be on the XZ plane, and then it's going to extend along the Y axis. Alright, so the best way to do this is to define variables. So the starting position in the X direction would be the width of the waveguide divided by 2, because we want it to be centered. So for that, we can create a variable. So if you just follow along, it's going to make sense later. So we can go waveguide width over 2. And notice the minus sign here, because I'm going to go onto the positive region when I define the size. And then for the Y dimension, I'm going to start it at Y equals 0, so that will just be 0. So comma 0. And then for Z, I'm also going to start it at 0. So not exactly centered on the origin, but centered in the width dimension. Okay, if you can't manage, then you can watch the video later on. and that's fine. No, it's okay. As long as you can watch the video after, that's fine. Of course, if there's too much lag for you and you can't follow along, then there's no point of you just staying here. That makes sense. So the video will be uploaded by tomorrow on the latest. Okay, I'll. So so you want to at the same time? Okay, I see what you mean. Okay, I will. I will make it. I'm just thinking because then it's not fair for the other ones because they would have to wait for it. Okay, let me think about it. I'll figure something out. I see what you mean. Okay, let me think about it. Um, but in any case, the video will be available tomorrow. Um, but you know, my thinking is the other group would also want a video at the same time, and I can't do that, right? Because they are the first ones to do it. But if you can't do it right now, that's okay. No problem. So in the recording, you guys are not going to be able to hear whoever I'm talking to, so it's gonna look weird. Anyway, so is anyone else having trouble, by the way, following along? I just want to have an idea. Okay. So yes, same thing I said. If you can't follow along and you prefer to watch the video later on, that's okay. All right. So those that can follow along, so we're at the waveguide design, and we're defining the starting position over here. So the starting position in X is going to be the width of the waveguide over 2, which is a variable that we're going to define in a little bit. And then the starting position in Y and Z is 0. All right, so if you click on enter, HFSS is going to ask you to add a variable because it doesn't know what WG_W is. So the best way to do it is to simply just type in the number and the unit, and then HFSS is going to recognize what variable or what dimension or unit you're talking about. So for the width of the waveguide, it's 15 millimeters. So if you go and just type 15 mm, then you can see if you press tab, HFSS is going to recognize that it's a length and that the unit is millimeters and the value is 15. So if you just click on OK. All right, so I think for everybody, the design is going to disappear. Don't worry about that. We're going to bring it back in a little bit, but just keep following along in the properties window here. So the size in the X direction will be the variable that we just defined. It will be waveguide width. The size in the Y direction, that will be the length of the waveguide, because I mentioned that we want the structure to extend along the Y axis. So you can create a new variable for that and call it waveguide L. And again, when you press enter, HFSS is going to ask you what's the variable. So in this case, the length of the waveguide is 10 centimeters. So again, if you type 10 cm and press tab, HFSS is going to say, okay, the unit is centimeters and it's a length. So you can click OK. And then finally, the Z dimension will be the height of the waveguide. So again, you can create a new variable called waveguide H, and the height of the waveguide is 7 millimeters. So if you go 7 millimeters, click OK. Yeah, we'll get to that in just a second. All right, so once you have the design, if you want to bring it out to the window, you can click on the solution space and then Control D on the keyboard. So Control D, that will bring out the design. All right, so now to answer the question where the variables are stored, if you click on the design, in the properties of the design, you'll be able to see the variables that we just defined. And the good thing about creating variables like that is we can go here and simply just change them, and the design will change with us. So if we say 5 centimeters, then you will see the waveguide shorten, and you can change any other variables whenever you can, whenever you want. All right, so 10 centimeters here. You can also change the view, so you can go isometric. And every time you want to see the full design, the shortcut is Control D. So if I let's say I accidentally zoomed in on the design, if I press Control D, it's going to show the full design. All right, so I'm gonna go back to create box in case some of you guys did not get what I wrote here. So these are the properties of the rectangular box that I just defined. So any questions so far? The length properties? Okay, so to get to see what the variables are, you just click on the design, so the rectangular waveguide, and then it will show you what variables here are inside that design. Hopefully that answers the question. If your question was how to get to like the properties of the variables, if you just double click on any of the variables, then you can see the properties here, and then you can change anything you want here, I guess. But if you've defined them correctly, then you don't need that. You can simply change the value. Okay, so if there are no more questions, I'm going to move along. So far we have finished the first step, so that is designing the 3D model. The next step is to define the boundaries for that model. Luckily for us, though, if we don't define any boundaries, HFSS will automatically assume that the boundaries that are not defined are perfect electric conductors. So in our case, we want a rectangular waveguide. So the boundaries of this waveguide, so that is all the faces, the 4 faces on the top, bottom, and the 2 sides, we want them to be metallic. So if we just leave it as is, we will still be okay. But just so that we go through the process, I'm going to show you guys how to define, instead of a peg boundary, which is a default, how to define a finite conductivity boundary such as copper. So that would be the next step. I want to define the 4 faces of the waveguide, so the top, the bottom, and this side and that side as copper. And then after that, we're going to define the ports or the excitations on the two sides of the waveguide here. All right, so to define boundaries, you have to select those boundaries. So there's a number of ways to do it. You can right-click and then go on selection mode, and instead of objects, select faces. Or you can see here, you can simply press F on the keyboard, and that will give you the option to select faces. All right, so I can select faces here, or you can simply press F on the keyboard. And once you do that, you'll be able to select faces over here. So to select multiple faces at once, you can press F and then Control, and then you can select multiple faces at once. You can also rotate the design to get to the rest of the faces, so I can rotate the design like that to get to but if you rotate it the way I did it, you're gonna have to press F again to be able to select. If you did it with a mouse, you wouldn't have to do it. You can just simply select the face. Alright, so I'm going to go back again to the isometric view. So if you press F on the keyboard, you should be able to select faces. So either press F on the keyboard, which is the fastest way, or you can go right-click, selection mode, and then press on faces. Either one will get you to where you want. And once you're able to select faces, we want to select the 4 faces of the waveguides that are not ports, that we want to define as copper boundaries. Alright, so if you Control, you can press F here, get the rest of the faces. So you should be able to select the 4 faces of the waveguide, so that as you can see here, the 2 ports of the waveguide are not selected. And once you have those faces selected, you right-click, assign boundary, finite conductivity. And once you select finite conductivity, you can give it a name, so we can call that waveguide faces. Then you can use material, and then you can search for copper. Once you have copper selected, press OK. And OK. And once you do that, you should be able to see under boundaries that waveguide faces was created as copper. Any questions so far? Does anybody want me to go over this again? Okay. Alright, so I'm going to go over defining the boundaries again. So I'm going to delete what I just had. If you've already done it, okay, yeah, that's fine. I'll wait a couple minutes. So I'm going to delete the boundary I just defined. If you've already done it, you can just leave it, but I'll just go over it again. Okay, good. So I will go over defining the boundary again. All right, so first step is you want to activate the face selection. So if you press F on the keyboard, you'll be able to select faces of the waveguide. So again, the goal is to select the four faces that are not the waveguide input or the output. So basically the four faces: top, bottom, left, right. So if you press F and you press Control E, you can select multiple faces. So we want to select the four faces that I just mentioned, so you can move the waveguide around until you're able to select all faces. And once you have the four faces selected, so again, you should be able to see through the waveguide just those four faces. If we right click, then assign boundary, then finite conductivity, you can see here that there are a number of options. You can define perfect E, so that's a perfect electric conductor. Perfect H is a perfect magnetic conductor, and then a number of other boundaries. There's also radiation boundary, and we're going to use that when we design the microstrip line. But for now, we want to define the boundary as copper, so we go under finite conductivity. For the name, you can leave it as is. I like to give things meaningful names. I'm just going to call this waveguide faces. You can manually define the conductivity and the relative permeability, but you can also select the material, which is the option that you will most likely go with. So you can select the material as copper. Then once you have copper selected, you can press OK. I don't know what this warning is. In any case, it did select copper. And then you click OK. And then under the project, you should be able to see the boundary we just defined and the properties of that boundary. So just to reiterate, if you didn't want to do that, HFSS would have assumed by default that the faces that you don't define are perfect electric conductors, which would still work in this case because it's a rectangular waveguide. But I just wanted to show you guys the process of assigning a boundary, and we're going to do that again for the microstrip line, which is the next design. It will only turn if I click on it. Like if I go under the design and I click on the boundary, then it would turn. But if you just click anywhere on the design, then it wouldn't show you the boundary unless you go and look at the boundary directly. No problem. Okay, so we have defined the boundary. The next step is to define excitations. And for the waveguide, it's really simple. The ports of the structure will be the input and the output of the waveguide. So it will be, actually, before I go there, I just want to show you guys, you can change the color of the design. So if you click on waveguide, you can change the color. So you can give it that color. You can also change the transparency. So sometimes you would want to see, your design might have things inside it. So if you want to see inside, you can make it more transparent. Things like that. So you can play a lot with the design. All right. Now the next step is to define the excitations or the ports. And again, for the waveguide, that will be this side over here, this face, and this face over here. So these will be the two ports of the design. So I will start by selecting the face that I want to define the port on. So if I just rotate the design here, I want to select this face. So again, if you press F on the keyboard, you should be able to select the face. So once you have that face selected, right click, assign excitation, and wave port. Alright, so now we're into the waveport properties window. For the name, again, I like to give it meaningful names, but for that we can just leave it as 1 because it's the first port of our design. Number of modes, since this is a rectangular waveguide, as you guys know, there's going to be a fundamental mode and then other modes that you can excite. For now, let's just say that we're interested in just one mode. So by one mode, it would mean it would just excite, in our case, the fundamental mode. If this was not a rectangular waveguide, if it was just a TEM transmission line, it would just excite a TEM wave. The integration line, you can just leave it as none. In some designs, you might have to define the direction of the electric field, but in this case, we can just let HFSS decide what mode to excite the waveguide with, and of course, it's going to be the fundamental because the number of modes is 1. So in this window, you don't really have to change anything, so you can just click next. Now, this option here for port renormalization is a very important option. You can either select do not renormalize, and when you select this option, it means that the port impedance will take on the impedance of the transmission line that it's connected to. So if you're connected to the waveguide, it will take on the impedance, in this case, of the fundamental mode. If you're connected to a microstrip line, it will take on the impedance of whatever that line is. So that's the first option, and I would say almost always you want to select do not renormalize, because a lot of times you either do not know the port impedance or you want to be able to see what the port impedance is. The other option is to renormalize all modes, and in that case you would fix the port impedance to a certain value. This can be good if you're designing something that you know would be connected to, let's say, a 50 ohm transmission line. So if you select renormalize all, it would fix the port impedance to a certain impedance, and then you'll be able to see reflections. So I don't think that we're going to use that option. Almost always we're going to select do not renormalize. Alright, so you don't have to change anything here. De-embedding, again, we're not going to use it, but sometimes you would want to measure the reflection or transmission characteristics a certain distance into the design, but for now we want to be able to see it at the edge of the design, so we're not going to de-embed to anywhere. Right, so basically you're not changing any of the characteristics, so you can just say finish. And again, if you go under excitations, you should be able to see the excitation that we just defined. Alright, so the next step is to do the same for this face over here. So it's the exact same steps as before. Right click, assign excitation, wave port. This will be the second one, it's okay. And then you're not changing anything here. Finish. Alright, so you have port 1 and port 2. Now, in order to see which one is actually excited, or which one the power input is going through, you can right click on excitations and then edit sources. And here you can see that the port 1 is the one that's excited with 1 watt of power, and port 2 does not have any input to it. So that means your structure is being excited with port 1 and not port 2, and that's just the default. It's the first port or excitation that you define in HFSS will be the one that has the power. So there's nothing that you need to change here. I just wanted to show you where it is. Okay. So far so good. Perfect. Okay. So we defined the excitations. The next step is to define the solution frequency and the convergence criteria. So that's an important step. So if you go over here under analysis, so under the design, under analysis, if you right click, add solution setup, and click on advanced. So there's a number of options here. So you guys will see that I'm going through everything very slowly because this is the first time. But of course, when you're designing this, after a while, you'll be able to go through the options fairly quickly. All right, so let's look at the options here. So this is the step where you decide a lot of things about the meshing, right? So you're going to tell HFSS how fine the meshing is going to be. You're going to tell HFSS what you consider an acceptable margin of error, and pretty much like what you as the user consider to be an accurate design. So that's a very important step in HFSS. All right, so the first one is the solution frequency. You can do a single solution frequency or multiple frequencies or broadband, we always use single. So the solution frequency here tells HFSS how fine the meshing is going to be. So the higher the solution frequency, the finer the meshing. So this frequency, you need to select it to be slightly more than the highest frequency that you're interested in. So let's say for this waveguide, you're going to operate it up to 15 gigahertz. So you want to set the solution frequency either 15 or higher, because the higher the frequency, the finer the meshing and the better the results. So the frequency here for the solution frequency has to be the same or higher than the maximum frequency of interest. Not the maximum frequency that the structure can operate at, is the frequency that you are interested in. Alright, so for the waveguide, let's say I'm interested in up to 15 gigahertz, so I can set this to 16 gigahertz. 15 would also be okay, but I cannot set it to 5, because otherwise that would not be a very good mesh. Alright, so that's the first option. The second option is the maximum number of passes. So the way HFSS does the meshing, it's called adaptive meshing. So it would mesh the design once, and then it would look at the error in the design and then see if that matches the error that you find acceptable. If not, then it would mesh it again, and every time it meshes the design, that's called a pass. So over here, you're going to set the maximum number of passes that HFSS is going to mesh the design before it gives up and says, okay, I can't find a solution. Of course, ideally, you want this to be as high as possible, but also you're not going to let the simulation run forever. So a lot of times we want to set this to maybe 15 passes. So we're going to give the software 15 chances to get the conversions that you want. If it doesn't, then you might have to rethink about how your design is made, or you might change a few things to get better conversions. Okay, so that's the maximum number of passes. And now maximum delta S. So maximum delta S is the convergence criteria. So that you can think of this as the maximum error that you allow in the design. So you can think of maximum delta S, where actually the delta S is the change in the S parameters. So the smaller this number, the better the convergence, or the higher accuracy your design has. So a lot of times we choose this to be 0.01. So this is an acceptable margin of error. If you're really, really strict, you can set this to 0.001, but that also means that your design will take longer to mesh. But for everything that we're doing, 0.01 is an acceptable maximum delta S. So just remember that number 0.01 is good. Maximum number of passes, 15 is acceptable. You can go higher. Again, all of that you will learn by experience, but for now you can use these as a starting point. Okay, so that's the first thing. Next is if you go under options. Now, the two things that we're going to change here is the minimum number of passes. So let's say HFSS runs through the design once and then it finds a convergence. Then it would say, okay, I'm done. But what you can say, okay, I actually want you to run for at least 5 or 6 passes, because I really want to make sure that the design is converged. So the minimum number of passes, we usually set it at around 6. So that means the design will run 6 times before it stops. Even if it converges, it would still run 6 times. And then the next one is the minimum converged passes. Almost always, you're not going to be happy with just one convergence, because it can happen that it can converge once as a fluke. So what you want is at least 3 converged passes, so that you're really sure that the design is accurate. So that means that HFSS will have to converge 3 times in a row before it stops the simulation, or before it says that this result is accurate. All right, so that was a lot of talking. So let's move along. So that's all you have to change. You can press OK. All right, so far so good with the conversions. I see. Okay, so you can't move it up. Okay, can you change the size? Can you like resize it like that? Yeah. You can press tab, and then once you get to what you think is okay, you can just press enter. No problem. Okay, so the next step is to define the frequency sweep. So again, this would be the frequencies of interest that you want to look, you want to view the results at. So like I said, there's three types: discrete, interpolating, and fast. A lot of times you want to run interpolating unless you are interested in fields, in which case you would run discrete. And I will show you guys how to do that in the next step. But for now, let's say we want to run an interpolating sweep from say 5 gigs to 15 gigs. And here the number of points, you can leave it as 401. The number of points here is not going to directly affect the simulation time because it's interpolating sweep, but if you're running discrete, you don't want 401 points because that will take a really long time. So an interpolating sweep, 401 points is okay, even if it was fast, but for the discrete sweep, you only want to run just a handful of points. Alright, so 5 to 15 gigs would be our frequency of interest that we want to look for, and just press OK. Alright, so I think that's it. We have everything we need to run the simulation. So if you go under simulation here, first you want to validate. So click on validate. You get these green ticks for everything. So you've done the 3D model, the boundaries, excitations, you've set the convergence criteria, you've done the frequency sweep analysis that you're interested in. We don't have any optometrics, and we don't have radiation, but that's okay. Alright, so once you have that, you just need to click on Analyze All. And then down here, if you say Show Progress, then you'll be able to see what HFSS is doing. So you can see it's going through all the passes here. So it'll take a minute or two because it's a fairly simple design. So any questions so far? Hopefully everyone is able to run the simulation. Good. Alright, so the simulation was done for me, but I'll give you guys a minute or two in case yours is taking a bit longer. Alright, so when your simulation is done, the very first thing you want to look at is the convergence. Because one thing HFSS is not going to do is tell you if your design hasn't converged. So that's something that you have to look for to make sure that the simulation is accurate. So to do that, if you go under Results, Solution Data, and then Convergence, then you'll be able to see the number of passes, number of solved elements. So that's how many tetrahedra, the ones we talked about in the presentation, that the design has been divided to. And as you can see, as the number of passes goes up, it meshes the structure even finer, which is expected. And then over here you can see that the target was 3 converged passes, which we specified, and then it actually converged 5 times, which is good. The target was 0.001, but as you guys can see here, it has met this convergence criteria for almost all of them. And even though it met it after even the second pass, because we specified a minimum of 6, it still ran up to 6 passes. You can also view this on a plot. So you can see this is our convergence criteria, and we've passed that for every single pass of the design. So when you see that, that means your design is accurate. And for the first few reports, I'm going to ask you guys to show me this graph, just so you get in the habit of looking at the convergence criteria before you trust the results. All right, so once this is good, you can close it. Now let's look at some results. The results will be here. So if you right-click on results, create modal solution data report. There's a number of ways you can view the results. You guys are familiar with the Smith chart. You can look at the reflection on the Smith chart. You can put it in a table or a polar plot. But let's say we want to use a rectangular plot for this demo. So if you click on rectangular plot, over here you'll be able to see the number of parameters that you can plot. You guys are probably familiar with the S parameters, or the scattering parameters of any network. So in this case, it's a 2-port network. So we have 1 port here and 1 port there. So these are the S parameters of the rectangular waveguide. S11, you can think of it as the reflection. S21 is the transmission. And then S12 and 22 is just the same thing, but from the perspective of the other port. You can plot Y parameters, Z parameters, the VSWR. Port Z0 is the impedance of the wave port. You guys remember, when you selected do not renormalize, the wave port will take on the impedance of the waveguide. So you can look at that as well. You can look at the active S parameters, group delay, and a number of other things. But for now, we're only interested in looking at the reflection and the transmission inside the waveguide. So that would be the S parameters. The solution will be, so setup 1, sweep, that's the interpolating sweep. Should have given it a meaningful name, but that's the one. The primary sweep is frequency, so that would be the x-axis. And let's say we want to look at S11 and S21. So we want to look at the reflection and the transmission. So if you click on control, you can select both of them. And we want to plot it in dB. So you can go ahead and say new report. Close that. So you guys can see here that there is the cutoff frequency of the waveguide, which is expected, and it's around 10 gigahertz. So below that, there is no transmission into the waveguide. Are you guys familiar with that from 399? That this is going to be an evanescent wave. So there's going to be attenuation below the cutoff, and then after the cutoff here, we have perfect transmission down the waveguide. All right, so that's one result that we can look at. We can also look at the fields inside the waveguide, but you guys might be thinking that the sweep that we have, the interpolating sweep, does not give us the field data, and you would be correct. For the field data, we have to run a discrete sweep. So let's run a discrete sweep for just one single point, and let's select a point in the pass band here. So we can select something like 12 gigahertz, and we'll run a discrete sweep for that, and then we'll be able to view the field. All right, so if you go under analysis, let's look at the setup. If you right click on the setup, you can add a frequency sweep. And select discrete. So again, you do not want to run 401 discrete points for sweep, because that will run the simulation 401 times, and you will be waiting a very long time. Normally, you would want to run a single point or just a handful of points. So let's say we're only interested in 12 gigahertz, and I'm going to select save fields. If you don't select save fields, it will not save the field data. So you can either select it down here or up there, either one would work. Alright, so save fields, 12 gigahertz, single point, discrete. And then click on OK. And then again, if you go under simulation, you can validate it, make sure everything is good. We haven't really changed the design, so it would still be okay, and then click on Analyze All. So as you guys can see here, it's only running 1 point, so that was very fast. But I will wait a minute or two until everyone gets on the same page. So Basil, are there any questions in the chat? Yeah, go ahead. This one? Alright, so if you go, I'm gonna delete this one and just do it again for everyone. So if you go under Results, if you right click, Modal Solution Data Report, Rectangular Plot, and then I just selected S11 and S21 together, and then said Create New Report. So if you selected just one, it would just show you one. So you just make sure that you select both of them, and then you should be able to see the S parameters. No problem. All right, so hopefully everyone's single point discrete sweep has finished. So now let's look at the field inside the waveguide. So to do that, you want to select the object that you want to view the field inside. So in this case, it's just the waveguide. If you right click on that and say Plot Fields, you can plot the EH field, you can plot the current, you can plot the quality factor, but let's say for now we're only interested in the E field, and we want to look at the magnitude of the E field inside the waveguide. So right click on the waveguide, Plot Fields, E, Magnitude E. And then you get to this window. And one thing you'll notice is the only solution or the only frequencies that you can plot it at are either the solution frequency, which if you remember was 16 gigs, and this is just by default, HFSS will solve the fields at your solution frequency, and it will also solve it at the discrete sweep. So that was sweep 1, and you can see the frequency 12 gigs here. So you just have to select 12, and then magnitude E, and then just done. And you should be able to see the magnitude of the E field inside the waveguide, as you can see here. We can also animate that field. So under field overlays, you can find the field that you just plotted, and if you right click on it and click on Animate. Alright, so question to you guys, and you can think about this for a second. Which way do you think the field is going to flow? Is it going to flow down the waveguide this way or up the waveguide this way? So you can think about the answer to yourself. Alright, let's see. Yeah. Okay, if you cannot see 12, there's two possibilities. Either you did not select safe fields in the discrete, or you did not run a discrete. Either way, you can just do it at 16 and it would still be okay. You would still be able to see a similar behavior. So you can just select 16 and follow along for now. Alright, so for the animation, I'm going to go over this again. So you just go under Field Overlays, right click, Animate, and then you can leave the phase from 0 to 170, that's okay. So if you thought that it was going to go down the waveguide this way, you were correct. And the reason is we defined the power at this port of the waveguide, and that's why it's flowing down this way. Just so that we can see it, I'm going to change the power to the other port, and then you'll be able to see the flow going the other way. So if I go, and instead of port 1, if I put this as 0 and define port 2 instead to be the exciting port, if I run the animation again, then you'll be able to see it going the opposite direction. So the position or the port that you define the power can have a significance based on your design, of course. In this case, it doesn't really matter because it's a symmetrical waveguide, and the results are going to be the same either way, but just so you're aware. Okay, so that's the waveguide. Once you're done, make sure that you save it. So if you just click on the project and save, and you should also be doing this. Don't wait until you're done the design. Every time you do something significant in your model, make sure you save it, so you don't lose the results later on. Okay, so everyone's good so far. So that's the end of the waveguide, and we're going to move on to the microstrip line next. Alright, so we're going to go through the microstrip line, and I'm going to speed up a little bit because now you guys are familiar with the design process. But again, if you think I'm going too fast, please let me know, and I'll try to slow down. Alright, so we want to create another design. So we are already inside this project. We're not going to create another project, but we're just going to add a design to it. So if you go under desktop, you can add another HFSS design. And you can call it microstrip. Okay, so the waveguide example was fairly simple because there was only one object that we're simulating, which is the rectangular box. The microstrip line has a lot of objects. So we have the substrate, and we have the line on top of the substrate. And as you guys will see, we need a radiation box to define a boundary around the line, because as opposed to the waveguide, which was closed, the microstrip line is open to free space, so that we need another box on top of that. So we'll get started, and you'll be able to see what I'm talking about. Alright, so just like before, if you go under draw a box, and then just put a box somewhere in the solution space here. By default, it's a vacuum box, but of course we want this to be the substrate. It's called box 1. We can give that a meaningful name, like substrate. Alright, so we have the substrate. The material, we want it to be FR4. So if you select material here and go under edit, you can search for FR4. So the reason why I chose FR4 is because it's a fairly common substrate, and it's the cheapest one. If you guys have done any PCB fabrication, you may have come across FR4 or actually used it. So FR4 has a permittivity of 4.4 and relative permittivity, not permittivity. So it's epsilon R is 4.4, and the loss tangent is 0.02. So that's fairly lossy. So if you just select FR4, you can just click OK. Alright, so we have an FR4 box. The next step is to define the dimensions of the box. So it's the same procedure as before. We're going to define variables, and we're going to set numbers to those variables. So if you guys follow along, so again I want it to be sort of centered on the origin. So the X position, I would start it at minus sub width over 2. I can start Y at 0, and Z at I'll start at 0 as well. And the width of the substrate is going to be 50 millimeters. So click 50 mm. The unit is going to be captured by the software. And click OK. And again, don't worry if it disappears. We'll bring it back. The X size will be the width of the substrate width. Y size, so in this case I'm going to use a simple square substrate, so the width is going to be the same as the length. So Y size, I'm going to define it as sub W as as well. And then the height of the substrate, we'll define a new variable for that. We'll call it sub h, and it's 1.27 millimeters. If you're curious why it's this specific number, this is actually equivalent to a standard size in mils. This is either 50 or 25, I can't remember. But the 1.27 is actually a standard thickness for substrates, so that's why it's like that. You click OK, and then again on the keyboard, if you press Ctrl D, you'll be able to see the full design. So again, these are the properties of the box. The substrate width is 50 millimeters and the height is 1.27, and you can view the variables under the design here. So if you click on microstrip line, you'll be able to see the two variables we just defined. Okay, so far so good. The next step is to actually create a line and put it on the substrate. For that, you have two options. You can either use a box as a transmission line, or you can use a simple surface. So a lot of times when we're operating at low frequencies, the thickness is fairly small compared to the frequency or compared to the wavelength. So a lot of times we can get away with just using a surface instead of a box. Of course, a surface is not a physical thing that we can make, because it's just two-dimensional. But we can simply use a surface for now to define the line. Of course, in real life, this line would have a certain thickness, which would be the trace thickness for a substrate, if you've done any PCB fabrication before. All right, so the line we're going to use instead of a box, we're going to use a rectangle. So you can click on draw rectangle here, and just like before, just put a rectangle somewhere in the solution space, and we're going to set the dimensions in a second. Alright, so it's a rectangular box. We'll give it a name. We'll call it, it's not a rectangular box, it's just a rectangular surface. We'll call it microstrip. And as you guys can see here, there's a distinction between a 3D object, which is a solid that you can define a material, and a 2D surface, which is a sheet. And in a sheet, you don't define a material, you define a boundary. So that's the distinction between a boundary and a 3D solid object. So our microstrip line is over here. For the dimensions, actually, let's give it a different color so we can see it. So if you click on microstrip, you can give it a distinct color. So now you can see it. All right, so if you go under create rectangle, we can set the starting position. So we want the line to be on top of the substrate and also centered. So the position for X will be minus microstrip width over 2. Y will be 0. And then Z will be the height of the substrate, right? Because the substrate is not starts at Z equals 0, and then it goes into Z dimension, which is equal to the height of the substrate. So here will be sub H. And then the size in X, now we have to, of course, give the variable a number. So I've designed this microstrip line to be 50 ohms. And for that, the width is 2.43 millimeters. The X size will be the width of the line. And the Y size will be, we want it to be as long as the substrate, so it will be the width of the substrate. Alright, so everyone should have this microstrip line on top of the substrate, and I'm leaving the dimensions here if you're still copying them. Any questions so far? of the microstrip line? Sure. Okay, so I can repeat it, but it's also here in the properties. So it's just simply the width of the line minus width of the line over 2 as a starting position for x, 0 for y, and since it's going to be on top of the substrate, the starting position in z will be just sub h. And then the size in x is the width, which is 2.43 millimeters, and the size in y will be the width of the substrate, which is 50 millimeters. Does that answer your question? Okay, so I assume everyone is on the same page. So we have a microstrip line, which is not assigned to anything right now. So if you run a simulation with a sheet that's unassigned, it will pretty much not exist in your solution. So of course the microstrip line is made of copper, so we can define that as the boundary for this line. So if you right click on microstrip, you can assign boundary, and then so you can either assign it as a perfect electric conductor, but we're going to be more conservative here and just say it's made of copper because that's what it's going to be. So we can say finite conductivity. So it's the same idea as before that we did for the rectangular waveguide. So we're going to just find copper here and just select it. I don't know why I get this warning, but it does find copper as the material. Alright, so here we'll just also give it a meaningful name. We can say this is the microstrip line. Okay, and if you go under the boundaries, you should be able to see the microstrip line as one of the boundaries. Okay, so now we have a substrate. We have the microstrip line. Now, if we try to run this, well, first of all, we can't run it because we don't have any excitations yet. But this line here, we want it to be exposed to free space, because that's how in the real world it would be just a line open to air. So in order to do that, we have to define a radiation box around the line and define the boundaries of that box as radiation boundaries. So that's what we're going to do next. So let's go ahead and create a box. Again, put that box somewhere in the solution space. That box is going to be an air box or a vacuum box. I'm just going to leave it as vacuum, and it's just a radiation box, or a rad box. Alright, so we want this radiation box to be the same size as the substrate because we want it to cover the line, and we also want it to be a certain height above the line. So for the height of the radiation box, usually you want it to be at least like half a wavelength away from the top of the line. So it has to be far enough so that it's actually open to free space. So let's set the dimensions with that in mind. So the starting position will be the same as the substrate. So it's going to be sub W over 2, 0 and 0. Actually, let's before going there, I'm going to just make it transparent so we can see inside it when it goes on top. So I'm just going to make that fairly transparent so that we can see inside it. All right, back to here. X size is going to be sub width. Y size will be the same thing because it's a square. And then over here, the size of the box in the z axis, I'm going to define it as a function of the substrate height. But maybe that's an exercise for you guys. I want you to go back and verify that this would be at least half a wavelength or a quarter wavelength at the frequency that you're looking at. But for now I can define it as let's say 8 times the substrate height. This may or may not be optimal, but it will give us something that we can work with. Maybe this looks kind of small. Let's do 12 times substrate height. So it's high enough above the microstrip line. So far so good. Okay, so now the next step is to define the boundaries of this box as radiation boundaries. But before I do that, for any microstrip line on top of a substrate, the bottom is going to be a ground, as you guys know. So in this case, I have an option to define the bottom of this substrate as copper in terms of a finite conductivity boundary, or I can also just leave it without defining any boundary, and HFSS is going to assume that it's a perfect electric conductor. And for almost all cases that we're going to be dealing with, that is a fairly good approximation. So in this case, I'm just going to leave it undefined, knowing that HFSS will assume that to be a perfect electric conductor. So we will get the ground on the bottom here. So the only thing left is to define the rest of the 5 faces of this radiation box as radiation boundaries. So to do that, we press F on the keyboard so that we're able to select faces. And I'm just going to go around, select the 4 sides and the top face so that I can define them as radiation boundaries. So I'm just going to select this one. Select this face. Face, and then finally select the top face here. Alright, so once you have all 5 faces except the bottom selected, you can right click, assign boundary, and radiation. And good thing about the radiation boundary is there are no options because it's simply an open boundary. It's open to free space, so you can just click OK. Okay, so we have the radiation box. The next step is to define the ports, and for that you have 2 options. The first option is to so actually, let's think about the wave port before going any further. So we want the wave port to be able to excite the transmission line as something would in real life. So if you're using a microstrip line in the lab, you would normally excite it with something like a coax cable, which is something that we're going to do in the second lab of the course. We're going to do that with a coax cable. But what you want is you want to define, put a wave port such that it can excite this line. So the wave port has to be big enough to excite something called the fringing fields of the line, which you guys are probably familiar with. So the fringing fields are around the microstrip line. So the wave port has to be big enough in order to be able to capture those fields, both in exciting the line and in receiving the power from the line. So one option is you can define this whole face as the wave port. Some of you guys might be thinking, okay, we just defined it as a radiation boundary. So a wave port in HFSS takes precedence over radiation. So if you've already defined as radiation, you can still define it as a wave port. But what we're going to do is actually create a surface and define that surface as a wave port, which is a more elegant solution to this. But you can also, one option is you can define the whole face here as a wave port and the whole face over there as a wave port. But we're going to go with another solution. All right, so we are going to create a rectangle to define the wave port on. So you can say create rectangle, and the wave port is going to be in the XZ plane. So right now we're drawing in the XY plane. So if you go over here, instead of XY, you can just select HZ. So we can just put the draw the rectangle anywhere for now. And as you can see here, it's an unassigned sheet. We're going to give it a name. Call it port 1. And now let's look at the position. Okay, I'm going to change this back to the XY because it's just nicer to look at. Okay, so there are there's a rule of thumb in designing a wave port for a microstrip line. Again, like I mentioned before, the idea is it has to be big enough, both width-wise and height-wise, to be able to capture the fringing fields on the transmission line, or in this case on the microstrip line. The rule of thumb is the width of the port has to be 6 times the width of the line, and the height has to be 6 times the height of the substrate. Alright, so with that in mind, let's set the dimensions. So for the position, we want to go minus wave port width over 2, and it's going to be at y equals 0, and it's going to start at z equals 0. Okay, for the width of the wave port, like I said, we want it to be at least 6 times the width of the line. So you can call variables inside other variables. 6 times the width of the line. So here it's going to be wave port width, and then the height, we want it to be wave port height, and we want it to be at least 6 times the height of the substrate. So 6 times sub h. All right, and that defines the wave port here. Alright, so I'm going to click on the properties again so you guys can see them. This is the starting position. The width is 6 times the width of the line. The height is 6 times the height of the substrate. Are there any questions? Which side to select? Can you elaborate? Oh, the radiation box. Okay, so the radiation box, it's 5 sides. So it's this one. So the 4 sides of the box. So 1, 2, 3, 4, and then the top. So 5 in total. Okay. Alright, so we have defined one wave port so far. We also need to define another wave port on the other side, but instead of having to go through the whole process again, I can just copy that one and then simply change the Y dimension. So you can Control C, Control V. So if I Control C and Control V, I can just replicate it. And then I'm going to go on the second one, and instead of having it at y equals 0, I'm going to have it at y equals sub w, so that will simply move it across to the other end of the substrate. So all I did is I copied that one, and then instead of having it at y equals 0, I just changed it to y equals sub w, so that just moved it across. You can also do some mirroring if you want, or you can literally move it. You can edit and duplicate along the line. So there's a lot of things you can do if you've used any CAD software. A lot of things that you can do in CAD you can also do here as well. But here I just simply copied it. Alright, the last step is to actually define these surfaces as excitations, because right now they're just unassigned. So if you right click on the first one, you can assign excitation, wave port, and again just leave the default settings. We're not going to renormalize. So this would be a place where you might want to renormalize, because if you have a 50 ohm connector, you want to fix the port impedance 50 ohms just to see any reflections. But for now, let's say we want to see what the port impedance. We want to see what the impedance of the transmission line is. So we're just going to leave it as not renormalized, and do the same thing for the other port. Some excitation. And over here you can see they came under wave port, and if you look under excitations, you'll be able to see 1 and 2 as well. Alright, so that's it for the excitation. Next step is to set the frequency sweeps. So again, if you go under analysis, well, actually we have to set the solution setup and then the frequency sweep. So analysis, solution setup, advanced. So you get to the same window as before. Again, the solution frequency is going to be the maximum frequency of interest. So let's say I'm going to run this line from 1 to 3 gigahertz. So I will just leave it as 5 gigahertz because that's higher than 3. Maximum number of passes, I will put that as 15, just like before. Maximum delta S, again 0.01 is fairly good. Actually, another point on that, when you're running the design, if you're going through a number of iterations, just use 0.01, but just before you fabricate it physically, you might want to go to a lower maximum delta S so that you're sure that the design you're going to fabricate is correct. So that's something that you're going to learn as you go along. But again, 0.01 is still good. Under options, minimum number of passes, I like 6, and for minimum conversion, 3 is usually good. So again, you want to make sure that the design, the conversions was not just a fluke, that it actually is consistently converged through three consecutive passes. Okay, then you get to the sweep type. Again, interpolating is what we're going to use the most. So let's say I'm interested from frequencies from 1 to 3, and for 1 point is okay. Alright, once you have that, you can click on simulation, validate. Everything's in the green, and then analyze all. So question to you guys. Right now, we have chosen the port impedance to be the same as the impedance of the line, and when we chose do not renormalize, basically the impedance of the port will be the same as the line. So with that in mind, do you guys expect any reflections? So if you look at the S11 when the simulation is done, do you expect to see reflections, or do you expect to see flat transmission through the line? So just think about that as the simulation is running. Okay, so it's done for me, but I will wait another minute just in case it's still running for some people. The line. Okay, can you see it now? Okay, so again, this was a simple design, so it shouldn't take a long time to simulate. So let's look at the results. So just like before, I'm going to plot the S parameters. So right click, create modal solution data, and rectangular plot. And then I'm going to select S11 and S21. Alright, so if you remember your answer to that question, are we expecting any reflections in the line? And the answer is there's going to be no reflections. And the reason for that is we enforced a matched port. So if you guys remember that in order for perfect matching to happen, or for maximum power transfer to happen, the port impedance and the line impedance have to be the same. And since we enforced the port impedance to be the same as the line, we are not going to get any reflections regardless of the size of the line. Had we enforced the port impedance to be a certain value, then the S parameter calculation will be done with respect to the impedance that you define. But here we're not going to see any reflections because the system is matched. Alright, so the green is the S21 or the transmission, and the red is S11 or the reflection, so the reflection is very low down the line. Now one thing we can actually see here is the actual impedance of the transmission line. So if you go under modal solution data again, you can plot port Z0. Let's plot the real value of that. And here you can see that the impedance of the line across frequency is almost 50 ohms. So I designed the width of the line to be 50 ohms, and that's why we're getting that. Of course, if you chose a different width of the line, then this number would be different, but the S parameters will be unaffected. And that's what you have to keep in mind if you chose to not renormalize the wave port. Actually, let's run a parametric sweep before we move on to ADS, so you guys can see the change in the port impedance. So I'm going to go ahead and do that. Is everyone done the simulation and is on the same page here? Any questions on the chat, Basil? Okay, sounds good. So we're gonna do a parametric sweep of the width of the line and look at the results here for the port impedance. So to do a parametric sweep, you go under optometrics, right click, add, and parametric. So again, optometric, right click, add parametric. So you get to this window, you can add. So the variable that we want to sweep is the width of the transmission line. So in this case, it's just the width of the line, so it's MSW. And let's say we want to run it from 1 millimeter to 3 millimeters in steps of say 0.5. So here, linear step 1 to 3 in steps of 0.5. So if you add that, so make sure you click on add. If you don't add, then it will not go. So just add it, click OK. And if you go under table, you will be able to see all the variations that we're requesting. So we're requesting width of 1, 1.5, 2, 2.5, and 3. And keep in mind that we have defined the wave port to be a function of the width of the line. So the wave port will always be 6 times the width of the line, which means it will always be big enough to capture the fringing fields that we talked about. And that's one of the good things about defining things in terms of variables. You can do these kind of sweeps and not having to go and change the design manually every time. Alright, so if you have the sweep defined, you can click on OK. So the sweep, parametric sweep should be defined here, and it's enabled. So you have two options. You can either go under simulation and click on analyze all, or if you have multiple sweeps and you only want to multiple parametric sweeps and you only want to run one, you can simply right click on the one that you want to run and say analyze. But in this case, since we only have one, it's going to analyze it anyway. So I'm just going to click analyze. So over here you can see that it's going to run 5 different simulations. Each one of them is going to run after the other. There is a way to make them run in parallel, and I will show you guys that maybe next time, or I will upload a document showing how you can configure HFSS to run multiple simulations in parallel, because the servers can handle it. But for now it's going to run them one after the other. So we'll just wait a minute or two until it's done. But there is a way to make them run all simulations in parallel. Okay, so it looks like it's done for me, but we'll wait. I'll wait a minute or two. Okay, one thing you can do, even if you're still waiting for it, is just follow along. So what I want to do is I want to see the port impedance for all the variations that I just plotted. So if you go under the plot for the port impedance, you can add the other variables as well. So if you go under families, you'll see the variable here, and the value nominal means it's the one that you select in as the variable in the variable window. If you go under edit, you can see all the variations that the simulation has results for. and if we select all of them and just apply trace, you'll be able to see the port impedance for different line widths. So as you expect, if you reduce the width of the line, the impedance is going to increase, and that's the characteristic impedance of the microstrip line. So I'm just going to go over that again. If you go under families, you'll be able to see all the values for the variable that the simulation has results for. If you select all and apply trace, you should be able to see all of them here. And would you guys expect the S parameters to change as you change the width of the line? You can think about that answer. So if I plot the S parameters, let's say at 1 millimeter, would they change? So the S parameters are not going to change. I actually should have created a new report. Let me delete that and do it again. Alright, so here, and I want it at 1 millimeter. So if you remember the S parameters from last time, the S parameters have not changed, and again that's because the port impedance is going to take on the same impedance as the line, so you do not expect the S parameters to change if you select it. Do not renormalize for the wave port, which is what we've done here. Okay, so we are I think done with HFSS for now. I wanted to show the coax cable, but I think we are running out of time. So one thing you want to do is save your design after you're done, and pay attention here. Once you're done your simulation, if you're not running a simulation, make sure you close HFSS, because if you have HFSS open, you're hogging a license, and we have a number of courses that are using the software, and we have a limited number of licenses, so we don't want to be hogging a license if we're not using it. So make sure you close the software. And one other thing I wanted to tell you is about the results. So if you go on to the folder where you have the project, there are two important files. There's the project file, so that is the project, and this has everything you need to produce your results. So if you're running through problems and I tell you to send me your HFSS design, all I need is that file. So it's an AEDT file. It's called ANSYS Electronics Desktop file, and it's a fairly small file. The results here, that folder which has the results, it can get very big very quickly, and that's because all the results that you run in the simulation will be stored on there. And this file is not really important because you can always reproduce the results using the project file. So periodically, every 2 or 3 weeks, I want you guys to delete the results, because if you're using any of the drives on the server, they get full fairly quickly if a lot of people are running a lot of simulations. So when you're done, just delete the results file. It's not important, and if I ask you to send me an HFSS project, do not send me the results, because I can always reproduce them on my end. So just make sure you delete that file every now and then, because the H drive can run out of space fairly quickly. Okay, so if you're done that, we're gonna take a 5-minute break, and then we're gonna come back to ADS. You guys wanna get a sip of water or something? So we'll get back here at 4:40, and we'll continue with ADS. All right, so the lab here has no report. You don't need to send anything. The reports are gonna start from lab 2. So lab 2 will have a report that'll be in 2 weeks for you guys. I will upload the HFSS projects just for this lab, so you guys can see what I've done. But no, to answer your question simply, no, there's nothing due for this lab. So you said if you want to run through the like the program. Okay, so I will upload, or I think I already uploaded. There's an introduction to HFSS document. That could be good. There's also the HFSS manual. I can upload it, or you can actually access it from the software. So if you go under HFSS help, there's the manual PDF document. I can go ahead and upload that on CLearn, but you guys can access it from the software as well. Also, no problem. Also, there's a lot of specific tutorials on YouTube, or you can also ask me. I'm more than happy to help. I don't know a specific channel. No, not on top of my head. You might find some popular channels. I don't know them by name. Okay, guys, I'll be back in a second. All right, guys, welcome back. So we'll start on ADS shortly, but I just wanted to give you an overview of the software. So it's an electronic design automation software. It's really good for circuit analysis, and it allows you to optimize RF circuits fairly well. It does perform electromagnetic field simulations, and it's faster than HFSS, but it's also less accurate. So we'll try to, in some of the designs we're gonna make, we're gonna try to compare ADS and HFSS. and we'll see that HFSS is slightly more accurate than ADS, but also takes a lot more time, as you guys have seen. So in the time that's left, I think I will show an attenuator and a microstrip line on ADS. So let's get started with that. So you guys can see my screen all right? Good. Okay, so ADS is advanced design system. So if you search for advanced design systems 2020 update 2, that should be the one. You can also find it on the desktop. So you can click on that. The license will expire in 9 days, and we are doing something about it. So you can close that. So you can say that you're new to ADS. It's gonna show you some pointers as you go along. Could not create workspace. Okay, I don't know if you guys got the same error, but it didn't want to create a workspace for me. But I'm gonna create one now and see what happens. So I'm gonna create a workspace and call it ADS workshop. And again, I'm gonna put it on the D drive, on the H drive. If you guys don't have an H drive, you can use the D drive as well. Alright, so I have a workspace. We're gonna use mostly schematics in the course, so you can go on File, New, and Schematic. It does seem to have trouble doing things for me. Okay, I'm gonna open this on a different server because I'm getting an error. Is anyone else getting an error, or are you guys okay? Alex, you're getting an error? Okay. Or maybe that was an answer to another question. Okay, I will, I just ran a different server, and hopefully that works for me. But I'm gonna assume that you guys are doing alright. I'm gonna create a new workspace. Alright, so hopefully this works. So you guys will probably have a workspace, so it's probably an error just on my end. So if you go under File, New, and Schematic, you'll be asked for a name. So the first one we're going to design is an attenuator. So you go and create schematic. Alright, so there's a number of things that you can do here. What I'm going to show you today is to place components on the schematic, connect components together using the wire here, run a simulation using this gear, and then do some tuning with variables. And you can also add some grounds. let's get started. So the attenuator that we're going to design is a 3 dB attenuator with an input impedance of 50 ohms. I already know the variables, but there are online calculators that can tell you resistances for either pi or T attenuators. So by default, the window here shows the basic components that you need, but there are also other options. For example, the transmission lines are here for microstrip or ideal. We're going to use microstrip in a little bit, but for now let's just stay in lumped components, and we're going to add 3 resistors. So you just click on resistor. You can add 1. If you press Ctrl R on your keyboard, you can rotate components. You can add 1 here and 1 here. And then I'm going to add grounds. So I'm going to insert a ground over here and over here. And then I'm going to connect them with wires like so. And then escape to just not have the wire function anymore. Okay, so everyone should be able to get that. So it's fairly intuitive. You just add resistors. If you want to rotate it, Control R on the keyboard. All right, so for the resistance values, the series resistor will have will be 18 ohms. The shunt resistors will be 300 ohms. Alright, and that's the basic circuit that we want to simulate. So in order to actually simulate it, you have to define ports and simulation blocks. So you wanna tell ADS what kind of simulation you want to run. For us, that will always be an S parameter simulation. You also want to define some ports. So a port in the equivalence in real life will be the connector that you are using to connect to the circuit. So this is a 2-port network, so there's going to be 1 port on this side and 1 port on this side. In ADS, this is called termination. So you can either try to find components here, or you can also search for components over here. So if I search for term, so this is the abbreviation for the block. It's port impedance termination for S parameters. So if I click on that, I should be able to add these terminations. And again, these will be grounded. And will be connected with wires to the circuit. So what this means is that this circuit will be connected to a 50 ohm connector or transmission line on both sides, and we want to see the scattering parameters of this circuit based on these connections. So now we want to add an S parameter block simulation. So you can search for S param is the first result here. So you can click on that. Escape. And in the S parameter simulation, you define the frequency range. So let's say we want to look from, let's say 1 to 3 gigs in steps of let's say 0.001. You can also double click on the block and define the step sizes. So here you can see that's a lot of points. In ADS, that's okay because it's fairly fast, but of course you wouldn't want to do that on HFSS. Like 20,000 points is way too many points. You can just decrease that to by a little bit. So let's say 0.01 gigahertz. It's only 2,000 points. And click OK. All right, so you have the S parameter block. You have the circuit. So that's the network that you want to characterize, and you have terminations of 50 ohms on the output and on input. Once this is done, you can click on this gear here, and that will simulate the design. And you guys will see this. It's almost instantaneous. It solves it very quickly compared to HFSS. All right, let's look at some results. So just like HFSS, you can there's different ways to view results. You can use a rectangular plot, or you can use a Smith chart. You can put it in a table format or a list. Let's say we want to view the S parameters in a rectangular plot, just like we did before. So if you click on rectangle plot, you can put it here. Let's say we also want to see the reflection and transmission, so we want to add S11 in dB and S21 in dB, and click OK. And as you guys can see here, I designed this circuit to be 50 ohms. So since the connection to the circuit here is 50 ohms, the connection on the output and the input is 50 ohms, we are going to have a perfectly matched circuit. So the S11 here is very low, it's perfectly matched, and the S21, which is the transmission, we can check the value if we put a marker. So it's minus 3 dB, and again, that's expected because I designed a 3 dB attenuator. Alright, one way we can view the results is to also add a Smith chart. Usually we use a Smith chart to look at the reflection characteristics, so I can add S11. And based on what you guys saw, where do you expect the S11 to be on the Smith chart? Think about it, think about the answer. And if you thought it was going to be right in the center of the Smith chart, you would be correct, because the system is perfectly matched to 50 ohms, and the Smith chart is normalized to 50 ohms. So the reflection or the S11 on the Smith chart is right in the center of the Smith chart. Okay, that's good. Now let's create some variables so that we can do some tuning and see how the results are affected. So I'm going to go back to the circuit, and I'm going to add a variable block. So it's called var. So I'm just going to add this block here, and if you double click on the block, you should be able to add a number of variables. So the first variable I'm going to create is R series, which is going to be the series resistance, and as a starting point, I'm going to say that's 18 ohms, or just 18. It's going to take the unit from the definition in the component, and I want to enable tuning for this variable because I will tune it later on. So if you go under tune, you can enable it, and maximum minimum you can just leave them for now. We can change them later on. Go ahead and say okay. Then we can so this is already added. You can add another variable and call it R shunt, and that one is 300 ohms. So if I say add, it's added, and then the minimum value here cannot be 9 because it's let's say the minimum value is 200 and maximum value is 400 in steps of sleep time. Alright, so if you're following along, I created two variables, R series and R shunt, and I enabled tuning for both of them, as you can see here. Any questions? Okay. So now I'm just going to rename, I'm going to put the variables here instead of the numbers. So for the R series, I'm just going to rename R series, and the shunt, I'm going to call it R shunt, and R shunt. Okay, so now what's cool about this is we can go under the fork here. So this is called the tuning fork. And we can tune the variables and look at the results at the same time. So if I click on tuning, it brings out this tuning window. And if I bring the results from before, just if I can put them on the same, let's see here what's happening when I change either of them. So now if I change the values of the variables, I should be able to see the results right away. So if I increase the shunt resistance, you guys can see the reflection is getting worse and worse, and the attenuation is also changing. You can see the point on the Smith chart is moving away from the center, which means now the design is mismatched to 50 ohms. If you hit the maximum, you can just change the maximum value, change to 40, you can keep increasing it. You can play with the other component and see how that affects your results. So you guys can see here that changing variables and tuning in ADS is fairly fast, which is not something you can do in HFSS. In HFSS, you have to set a parametric sweep if you want to look at different results, and you have to wait for the simulation to finish and then look at the results. In ADS, it's almost instantaneous, the calculations, but they are slightly less accurate than HFSS, so it's just something to keep in mind. And we normally don't use ADS for any antenna simulations or heavy electromagnetic simulations. We use it mostly for circuit analysis or microstrip lines that have sort of a closed form analytical solution that can be calculated fairly fast instead of having to solve Maxwell's equations like we do in HFSS. Okay, so that's all I wanted to show for the attenuator. We're not going to be designing circuits in the course really, but I just wanted to start with a fairly simple example showing the tuning that we can do and viewing the results on ADS. Okay, so if you're done that, you can, so if you close the tuning, it's going to ask you, do you want to save the tune values back to the schematic? You can say yes or no. I'm going to say no because the design was good as is. Close that, and I can save the results. If I want to take a look at it later, I can save this schematic and close it. Alright, so the next schematic we're going to, or the next design we're going to make is a microstrip line. And that's something that we're going to ask you to design in the course. There's going to be some quarter wave transformers, power dividers using microstrip lines. So that's what I'm going to show now is more relevant to what we're going to be doing later on. So you can go ahead and create another schematic. So create new schematic, and you can call that microstrip line. Create schematic. Alright, so for a microstrip line, it's similar design idea as before, but instead of having an attenuator circuit, we're having a microstrip line as our the network that we're trying to characterize. So let's add the basic things from before that we're familiar with. So we're gonna need some terminations on either side. So this would be term. Okay, so this would be term, so we need to add two terminations here. We're going to add the grounds to these terminations. Just checking, can everyone still hear me and see the screen? Okay. Alright, so we added the terminations. We're still going to run an S parameter simulation, so we go S param, so add it here, and let's say we're interested again from 1 to 3 in steps of 0.001. Alright, so now what's left is to add a microstrip line, and for that you need to first of all add a substrate block. So the microstrip line that you're going to design will need some substrate properties that it's going to go on. So let's add a substrate block. So for that it's called M sub. Go on here, microstrip substrate. You can add that block, and once you click on it, it's going to ask you for the technology. Let's work with millimeters. Say finish. And over here, that's where you define all the properties of the substrate that you're going to work on. Just going to move this down here. So the two most important properties are the permittivity, or the relative permittivity, the height of the substrate, and the loss tangent. So if you guys remember from FR4, let's say we're going to use an FR4 substrate, the relative permittivity was 4.4. The height of the substrate was 1.27 millimeters. So again, here if you chose the mil technology, you'll be able to define it in mil, and I think you can actually also define it in mil here, but the default is millimeters. And the loss tangent was 0.02. Alright, so once you've defined the substrate properties, what's left is to add the microstrip line. So the microstrip line block. What I've been doing so far is I've just been searching for the names because I know them, but if you guys don't, you can always go over here and look for the library that would have the component that you want. So if you know that you're looking for the S parameter simulation block, you can just find it here. If you're looking for a microstrip line, you can probably find it here. So if I click here, I'm able to see all the different types of microstrip lines that I can add in this circuit. And the one that I'm interested in is the MLen. So you can either find it this way, or you can simply go in here and search for MLen, and you'll be able to find it. So once you do this a few times, you can also go in the help. You can press F1 and then search in the help document what type of line or circuit component you want to add, and it's fairly good in helping you get there. Alright, so MLen is the one that I'm interested in, so I'm going to add it here, and you guys can see that by default it selected the available substrate sub 1 as a substrate, but sometimes in your design you may have more than one substrate, so in that case you'd have to create different substrate blocks. But in this case it just chose the one that's available, which is okay because that's what we want. Now the width of the line is of course the dimension that determines the impedance of the line. So if you guys remember from HFSS, the 50 ohm was 2.43, so I'm just gonna use that as a starting point. The length is just how far it goes on either side. So for that you can select let's say 50 millimeters. And what's left is connecting it to the termination blocks. So this would be akin to having a microstrip line on a substrate in the lab, and then connecting it to 50 ohm connectors on either side. So like SMA connector here, SMA connector here, characterize this transmission line, microstrip line, like in terms of S parameters. So that's exactly the same thing we're doing here. If we were in the lab, one of the labs would be, we would have a microstrip line on a substrate, and then you guys would measure it using the VNA, which would give us the S parameters, but we're just adapting and doing that on ADS instead. Okay, actually, before I simulate it, let's define variables instead of numbers here. So instead of the width here, I'm going to define it as a variable. So I'm going to add a variable block. Also, variable block is available here if you don't want to search it from here. And I'm going to say ms width, and the starting is 2.43, and that's okay. And I want to make it tunable because I want to see the tuning as well. So let's make it tunable. So if you go under tune, I'm going to turn it on, and let's say minimum is let's do it like HFSS. Let's do 1 to 3, and let's say the step is 0.5. We can change that later too. Okay, so now we have the variable for microstrip width, and over here we can just change it to MSW, and we'll leave the length as is, but you can also have a variable for that if you want. Okay, so if you guys are paying attention, you'll notice that compared to HFSS, here I'm defining a certain port impedance. So I'm fixing the impedance of the terminations to be 50 ohms and 50 ohms. In HFSS, if you wanted to do that, you would have had to do not renormalize the waveport and then force the impedance to be 50 ohms. So that's the key difference here between the two simulations. In HFSS, we can choose to not select an impedance and just let HFSS take on the impedance of the line. Over here, as far as I know, that's not something we can do. We have to define a certain impedance so that we can do the measurements with respect to, or do the simulation with respect to. Okay, now what's left is to just simulate. Okay, let's ignore that warning for now. Alright, let's plot same results as before. So rectangular plot, we'll add S11 and S21. So we can add S11 in dB and S21 in dB. And again, if you guys were paying attention, this looks very similar to the HFSS plot. So the reflection here, it almost has the same shape. I don't know if the numbers are the same, but it does have the same shape. In some of the labs, I'm going to ask you guys to run both simulations and then superimpose the results so that we can see a comparison. So I can already see for a simple simulation such as the microstrip line, there's a very good comparison between the two. Alright, let's also look at the Smith chart. Let's say we're only interested in S11 in the Smith chart so we can see the reflection. And again, what do you expect S11 to be based on the low reflection? If you guess the center, you would be correct. It is right in the center of the Smith chart because there is very low reflection. Again, I designed the width to be 50 ohms, which is matched to the terminations, which are 50 ohms. Alright, now it's more fun if we do some tuning. So if you just find this fork here, click on the fork, and let's bring the results so we can see them. So now let's change the width of the line and see how that impacts the reflection. So in HFSS, the width of the line did not affect the S parameters because again the waveport was taking on the impedance of the line, but over here the termination impedance is fixed at 50 ohms, so we will observe a reflection the moment we deviate from 50 ohms. So if we go this way, right away you see that we're moving away from the center of the Smith chart. The reflection is getting worse. If we go a little bit higher, let's set the maximum value to let's say 6, so we can play with it a little bit. So as you go further away from 50 ohms in the upwards direction, so if you increase the width of the line, you're actually decreasing the impedance. And if you recall the Smith chart, it's as you go towards the left, the impedance is going lower. So if I keep going, it's actually becoming the impedance is less than 50 ohms, so you're going this way. If I go the other way, I go into the more than 50 ohms region of the Smith chart, and in both ways the VSWR is increasing, so that's why you see the reflection increasing. So of course ADS is a lot more less settings than HFSS, and it's easier to get to use it fairly quickly. But you have to remember that it's not rigorously solving Maxwell's equations. It's just solving analytical approximations of Maxwell's equations for these structures, as opposed to HFSS, which actually takes the structure and solves Maxwell's equations at every single point, and that's why it's taking a lot more memory and a lot more processing, and of course a lot more time than ADS. One of the things in this course is we're going to try to get you guys using both programs, which are pretty much industry standards for electromagnetics and RF circuit analysis. And I believe if you're taking 4502, you will be using ADS a lot. Okay, so I think that's all I wanted to show. I could show the filter, but it's a very similar design process. You're just simply using inductors and capacitors instead of resistors and microstrip lines. But I think this would be a good good place to ask you guys if you have any questions about everything that's gone down. I'm gonna save the design. I'm just gonna save it here. So I'm gonna go to the chat and try to answer your questions. And again, just for HFSS, when you're done, make sure you save the results and then close the window, because if you're opening it and not using it, you're just hogging a license for no reason. And over here, the results don't take a lot of space, unlike HFSS, so don't worry about deleting them. So when you're done, just make sure you close it. And just like I mentioned, I will be uploading the project files for this workshop, so the ADS and the HFSS project files. But I will only be doing that for this lab, so you guys can see what I've done. And hopefully this was a good introduction to the software. Is there going to be a document for this tutorial or just a video? I will upload a video of everything that went down since 2:30, and I will also upload the presentation that I just showed you guys. So this presentation will also be uploaded on CLearn. Alright, do you guys have any questions about ADS, HFSS, or about the course in general? Any general wonderment? So ADS is generally it's used for RF circuit analysis. So it would you'd use it for like designing amplifiers or mixers, and it does have an option that can simulate structures electromagnetically. So it can simulate microstrip lines and I think also antennas. But the difference between ADS and HFSS in terms of solutions is that ADS takes on some analytical formulas that approximate Maxwell's equations. So, for example, for the microstrip line, there are some formulas that approximate the impedance, the reflection, the transmission based on various parameters. So ADS would use those equations to calculate the S parameters, and that's why it's very, very fast. It's almost like MATLAB, it's just calculating an equation. HFSS, on the other hand, it's taking on the physical 3D structure, and it's breaking it down into smaller structures and then solving Maxwell's equations at every single point. And if you remember Maxwell's equations, there's a lot of differentiation, integration, summations, and then it has to go through this meshing process a few times to get accurate results, and that's why it takes a lot more time. But HFSS is definitely the choice if you're designing antennas, because it gives you the actual rigorous electromagnetic solution based on Maxwell's equations. ADS would be good if you're designing amplifiers, attenuators, any sort of circuit where the only electromagnetics really is just the connections between the components. So if you have a circuit on like on a PCB, and you have a bunch of components, amplifiers, regulators, and the only electromagnetics is connecting all these components together, so the only electromagnetics really is the transmission lines, then you can use ADS with confidence, because it has very good approximations for the responses of transmission lines using those analytical formulas I was talking about. Does that answer your question? Any other questions? Okay, yeah, go ahead. So I will post the lab manual a few days before the lab. You don't have to do a pre-lab for any of the labs. The structure, I'm thinking it would be, I will show you guys a demo of, let's say 50% of the lab. So there will be a few designs, and I'm going to show you how to do one or two, which will be included as part of the report. And then for the last design, this would be like an exercise that you guys can take home and do on your own, and that will be available to help outside the lab as well. I think so. It could change, but that's the idea I have now. Most of them will be this way. There's going to be a demo or a tutorial of some sort, and then you guys will have like a take-home kind of design. Question coming? So just out of curiosity, how much delay was there between the stream and what you add my voice, for example? Okay. Okay. How about recording tutorials before the lab and being available to help during lab time? I personally thought that doing a demo would be helpful, but now I'm thinking if there's a delay for everyone, that might be the better option. I will discuss with the professor and see if that's the better idea. To me, it doesn't make a difference if I'm recording it now or recording it later, but for you guys, if it's better to watch the video, that might be the better option instead of having to wait. Okay. Well, in that case, I think I might record the lab before and just be available to help during the lab. I will let you guys know if there's any changes to that. If we miss a single click, we have no idea how to get there. It was skipping for me in the stream, so it's sometimes hard to wait. Okay, it seems to be a fairly common problem. Okay, I might record the video, and if all of you guys think that's easier than doing the live demo. Okay, looks like I'm doing a video. Okay, all right. If that works for everybody, and again, I will be available during the lab time and outside. Okay, yeah, you can tell the professor, and I will tell him as well. No problem. All right, I will be available for a few more minutes if you guys want, but there's nothing else to say in terms of the labs. Thank you for coming, and I will either upload a video next time or see you. Probably upload a video. Looks like it's going that way. No problem, guys. Take care.